while we're talking about limits, we have to include some trigonometric limits. And let's see, we're going to start with some basic ones. Now the same rules apply as the other limit rules, so I always start with direct substitution, and if I get out a number, then that's the answer. And so what we can do here is we can at least try tangent of pi over 4, and there's no reason that we can't just figure that out, because when I plug in this, nothing bad, I'm not dividing by 0 or anything like that. So hopefully I remember that the tangent of pi over 4 is just 1. Okay. So that's the first one. So let's try another one. So the limit as x approaches pi of x secant of x. Now I really don't like secant, so I'm going to think of this as x over cosine of x, right? Because secant is really 1 over cosine, so I want to think of it like this. And let's see, if I put in pi, I will get cosine of pi, and that's not 0, so it's perfectly legal for me to just plug in pi here. So my answer will be pi over the cosine of pi is -1, so I end up with my answer as negative pi. So so I'm just direct substituting this time. There's nothing says that I can't, and I get out a number and everything is good. Okay, so the tangent as x approaches, or the limit as x approaches 3 of the tangent of pi x over 4. If I plug in 3 here, nothing bad's going to happen. I'll get the tangent of 3 pi over 4, which I know. This would be in the second quadrant where sine is negative. So this is -1, right? So up here I had the tangent of pi over 4 was 1 because sine and cosine are both positive here, but here in 3 pi over 4, that's in the second quadrant where they're opposite. Okay. Let's do one more that's a little bit more interesting. What if we have the limit as x approaches 0 of sine of x over cotangent of x? All right, now when I plug in 0 here, I get 0 on top, and cotangent is really, so one strategy for doing limits with trig is to switch them back to sine and cosine. So cotangent is really cosine of x over the sine of x. Okay, so if I invert and multiply here, I'm going to get, let's see, I'm going to multiply here. I've got sine times then the reciprocal here would be sine of x over the cosine of x. And so now I have sine squared of x over the cosine of x. And now, because I just have cosine in the bottom, cosine of 0 is not 0. So I can just pop in my 0 here, and I get 0 over 1, which is in fact 0. So if I have things, sometimes I get sort of a 0, or if this had been something different besides cotangent, I'll do one more of these. One of my strategies is to switch it back from sine and cosine and simplify it and see what I get. Okay. So let me just do one more like that. What, instead of cotangent, what if I had instead the limit as x approaches 0 of sine, I'll leave sine in the top, of x over tangent of x this time. Okay, so tangent of x is really sine of x over cosine of x, right? And so really this bottom, when I plug in 0 here, I get 0 over 1, which is 0. And sine is 0 in the top, so I really sort of get that 0 over 0 indeterminate form. And so really I want to use the same strategy as I did before to see if some things will simplify. So this is really sine of x over the sine of x times over cosine of x. And when I invert and multiply here by cosine over sine in the bottom, I have to do the same thing up here. I get cosine over sine, right? And my sines will cancel here and just leave me with cosine. So really, this limit as x approaches 0 of sine of x over tangent of x, right? This is indeterminate form. So this is one way to go about this, is to switch when you don't have everything in sine and cosines, switch it into sine and cosines and hope that things cancel, is really equal to the limit as x approaches 0 of cosine of x, which is then just 1 when I plug in 0, knowing my trig values. Okay, now sometimes things can't be solved that easy, so sometimes we have to employ a different strategy. So these are two important limits that we're going to use a lot that I think you should memorize, okay? And these are the limit as x approaches 0 of sine of x over x equals 1, and a limit as theta approaches 0 of 1 minus cosine of theta over 0 equals, or over theta equals 0. Now, if I were going to plug these in, I would get 0 over 0, which is indeterminate form. And the same thing here, because cosine of 0 is 1, so I get 0 over 0, and that's not equal to 0, that's indeterminate form. Both of these are proved using the squeeze theorem, which is in the next lecture, but they're a little bit complicated, so I'm not going to prove them here. I'm just going to say, okay, we know this, we're going to use it now. Okay, so this is the one that pops up the most, really, and then this one occurs a little bit less often, but this one I'm going to use over and over. And this one is extremely useful because it doesn't just work like this. I can also use it in things like this, okay? So I'm going to just show you why this works like this, but and you don't have to do it like this every single time, but just know that it does work. So I'm going to kind of show this. So this sine of x over x equals 1, the limit as x approaches 0, of course. I'm going to think of this as, I'm going to say that we're going to switch over. So I'm going to say that theta is equal to 4h, okay? So what I'm going to do here is I'm going to multiply the top and the bottom. Before I do the substitution, I'm going to take the sine of 4h over h and multiply it by 4 over 4, okay? And now I am going to switch this over. So I'm going to have 4, and now I'm going to do the substitution of the sine of theta over 4h is still theta, okay? And now I have the limit as h approaches 0, right? And here, if I look at this, right, if I take the limit as h approaches 0, then theta is also approaching 0. If you put in 0 here, theta will also be 0. So I can actually switch, instead of writing the limit as h approaches 0, I'll write that the limit as theta approaches 0 is of 4 sine of theta over theta. And this is, I know that this part is 1. Our limit laws say that we can actually do these separately. Actually, I could have put a 4 out here because the 4 is just a constant. So this ends up being 4 times 1, which is just 4. Now, you don't have to do this complicated substitution every time, but what this means is that if I can make this where this value here is matching this value here, then I get 1 as my limit. And since it's 1, the reciprocal also works, is the same. So I know that this is equal to 4 here. But if I had the limit as h approaches 0 of h over the sine of 4h, right? I could do kind of the same thing here and multiply my top. I always have to multiply by 1. So I'm going to multiply the top and the bottom by 4 here. This leaves me with a limit as h approaches 0 of 4h over the sine of 4h. Actually, 4 times the sine of 4h, okay? So then this means that's my 1, right? Because the reciprocal of 1 is still 1, and I get basically 1/4 times 1 equals 1/4. So this one is extremely useful because I can not only use it, like if I make this h match this, I know it's 1, but I can also use it as a reciprocal and it still works. Okay, so let's do a few more that are a little bit more complicated than that, or just one more that's a lot more complicated than that. All right, so this one is much more complicated. I have the sine of 3x over the sine of 2x and over x sine of 5x. And all of this as the limit as x approaches 0. So what I am going to do is I'm going to break this completely apart. So I'm going to think of this instead as the limit as x approaches 0 of sine of 3x times the sine of 2x times 1 over the sine of 5x. Now I haven't used this x here, right here, this x here. So it's in the denominator, so I'm just going to choose to put it right here, okay? So when I multiply this all back together, I get exactly this again. Now, I know from the previous example that if I can make this first one into sine of 3x over 3x, then I know that that limit will be 1, okay? So what I'm going to do with this one is I'm going to multiply. If I want the 3 down here, of course I have to multiply the 3 up here, okay? And now I know that this here is 1. Now both of these, I have a bottom and a top here. So I'm going to think of this. Now since I need an x down here and an x up here, then I can multiply essentially this whole thing by x over x, which is 1. So what I'm actually doing is multiplying the top and the bottom by x over x. Now I'm going to take the top x here and place it up here where I need it up here. And I'm going to take the bottom x and put it down here where I need it. Okay, so now I know that if I make this a 2 down here, then this whole thing, right, the sine of 2x over 2x would be 1. So I'm going to multiply the top and the bottom of this one by 2. And now I know that this part here is 1, the limit, right? And if I can make this 5 on top here, then that will also be 1. So I'm going to multiply this by 5 over 5. And now I know that this limit here is also 1. And so basically, now our limit law says we can evaluate each thing separately. So the limit as x approaches 0 of 3 is just 3, right? Then I know that this part here is 1. Then I have 2. Then this whole thing here is 1. And then this is, oh, actually, I didn't include this 5 here in my 1. So this would be 1/5 then times 1. And the whole thing, when I multiply it together, is 6 over 5. And so this is kind of an application of how we use this. All right. Until next time.